In this podcast, we'll be looking at ray diagrams and equations for convex mirrors. The convex side of a mirror is the part that sticks out, and this will be similar to concave lenses. I'm going to start by drawing a light ray that is parallel to the principal axis. When that light ray is reflected, it will be reflected in such a way that it appears to come from the direction of the focus, and the focus is on the other side of the mirror. So what I will do is draw a dotted line to remind myself that this light ray is coming from the direction of the mirror, of the focus, and bouncing off like this. So the light ray is going toward the mirror and then bouncing off like that. The second light ray that I can draw goes toward the direction of the focus, and when it bounces off parallel to the principal axis. Then, once again, I can draw a dotted line to think about what's going to happen when these diverging light rays, what they do to the observer. So here's the observer looking at these diverging light rays. And the observer is going to perceive that the diverging light rays come from a single point here on the other side of the lens. So in this case, the image will appear to be upright, and it's a virtual image because no light is actually converging at this location. It's an optical illusion. Here's my object. Once again, we're going to define P as the distance between the object and the mirror. Q would be the distance between the image in the mirror, and F is the focal length of the mirror. We can still use the same equation for mirrors. 1 over P plus 1 over Q equals 1 over F. Let's try another example. Find the image created by the object. So let's practice this again. I'll start with a light ray going toward the mirror, and then it's going to bounce off as though it's coming from the direction of the focus, like this. Again, I would point out that that is obeying the law of reflection. Remember that the law of reflection says that the angle of incidence equals the angle of reflection. So if I were to draw a normal here, you don't need to do this to solve the problem, but just to remind you, if I were to draw a normal, those two angles, the angle of incidence and the angle of reflection, would be congruent. Let's draw my next ray. My next ray is going to go toward the direction of the focus. Again, no light passes through the mirror, so I draw a dotted line. And then when it bounces off parallel to the principal axis. Again, the observer sees the light rays that are coming at the observer. This is why I draw arrows to indicate the direction of the light ray. And then the observer, again, sees this optical illusion of an upright virtual image. So if I follow these light rays back, this one and this one, if I follow those back, I end up with an image behind the mirror, upright and virtual. Let's take a moment to talk about mirrors, and in particular plane mirrors. Plane mirrors produce virtual images. It makes it look like there's an object inside or behind the mirror, but it's not really there. And plane mirrors obey something called the law of reflection. I drew an example of the law of reflection in this example, but let me do another one, maybe a simpler one. If we have a mirror. And if I have an observer here, and if that observer is looking at an object, maybe an object inside the mirror, what will happen is the light ray that goes to that person's eye will follow what's known as the law of reflection. And again, the law of reflection says that the angle of incidence, so there's a light ray bouncing off of the object, and remember there's light scattering in all directions off the object, but we're looking at a single beam of light, a representative beam of light, that happens to bounce off the object, and the angle of incidence equals the angle of reflection, and it hits the person's eye. And what it looks like to the person is that the object is actually on the other side of the mirror, and it is whatever the distance is from the object to the mirror, that's the same distance from the mirror to the image. So this is what the person thinks they're seeing. That's the illusion that you see when you look into a plane mirror. Following the rules of geometry, then, we have 3 congruent angles here. And we want to keep that in mind when we are drawing ray diagrams. Mirrors produce something called specular reflection, but many objects produce what's called diffuse reflection, which is when light is reflected in many different directions. It turns out that diffuse reflection is much better for driving at night, especially as people get older. Specular reflection can be very distracting, too shiny. And the weather conditions that cause specular reflection are rain, precipitation. If we think about what happens in the cases of specular and diffuse reflection, for specular reflection, essentially what you have is a very smooth surface. And if you have light rays coming in from a single object that's far away, and if those light rays are all parallel, like this, then what will happen is those light rays should obey the law of reflection. And what that means is the angle of incidence will equal the angle of reflection as measured from the normal. So let me put in some normal lines here. And then to really do this correctly, I would get out a protractor, but for the purposes of our notes, I'm going to sketch it. Again, this angle of incidence equals the angle of reflection, and all of these reflected light rays are going to bounce off so that they are still parallel. They're all following the law of reflection. So this one comes in, it bounces off. This one comes in, bounces off, and so on. Now, in the case of diffuse reflection, at the microscopic level, we have a rough surface. And now let's think about what happens when we've got beams of light that, again, are parallel coming in. Here are some parallel beams of light, and they're all going to follow the law of reflection, which means when I draw in my normal, first of all, you can see the normals are in all different directions because the surfaces are in all different directions. Again, this is at the microscopic level. So now, when I draw that reflected light ray, and when I obey that law of reflection, I say, okay, this angle of incidence must equal the angle of reflection. Well, that light ray is going to go off to the left there. But now look what happens with my next light ray. Angle of incidence, angle of reflection, it's going to be sent off to the right. This one's going to be sent like that, and the last one also has its own angle. So we say the light is scattered in all directions. And what this does is it produces what we call a matte surface. A matte surface does not reflect light or is not shiny. So to sum up, for our law of reflection, the angle of incidence equals the angle of reflection. When we draw reflected rays, what we want to do is extend the incident ray to the surface on the mirror. We're going to draw a normal line to the mirror. A normal line is 90 degrees. We're going to measure the angle between the normal line and the incident ray, measure that exact same angle on the opposite side of the normal line, and draw the reflected ray. I'd like to actually show you a trick to doing this even faster and without a protractor that will get you the same results. First of all, if your mirror is not long enough, you can extend it like I will do in this mirror example. So this is going to be a ray diagram for a single plane or flat mirror. Now what I'm doing is I'm measuring, and I'm seeing that this is about 1.8 centimeters. I'm going to put a dot on the other side, and I'm going to sketch my image. So when I sketch my image, I'm actually using a perpendicular bisector. The segment that I've created, the mirror, is the perpendicular bisector. Of a segment joining the object in the image. Then what I'm going to do is I'm going to draw a line between the observer and the image, because this is what the observer thinks they are looking at. Now there's no light passing through the mirror, but it looks like there is to the observer. And now I'm going to go from this intersection between the beam of light and the mirror, and I'm going to go back to the object. So, oops, I drew this arrow in the wrong direction. What I've just drawn represents a light ray that is coming from the object, bouncing off of the mirror and hitting the person's eye. And I want you to take a close look at this picture because it does obey the law of reflection. The law of reflection says that if I were to draw a normal line, which I'll go ahead and do, I'm just checking now, I don't have to do this part to solve the problem, but when I draw my normal line, the angle of incidence should equal the angle of reflection. And if I wanted to be really careful, I could check that with a protractor. Let's look at some questions. What if an incident ray comes in along a normal line? How would it be reflected? So basically what that's saying is, if I had a mirror, and if a person or if an eyeball were looking at itself, then the light would just bounce straight back. So it would be reflected along the normal. Here's another thinking question. How big does a flat mirror have to be able to see your entire body? Well, let's draw a little sketch. A person and a mirror. In order to be able to see their entire body, the mirror has to be half as tall as the person. At eye level, the light ray is going to bounce to the mirror and bounce straight back. In order to be able to see their feet, the mirror has to be long enough so that this angle comes down to the feet. So the way that I've drawn it here, it's not quite long enough. Let me try it again. Okay, so here's my mirror. We'll make it a bit longer. So what you want to, again, think about is you want to go from the eyes to the bottom of the mirror. And the law of reflection says whatever angle we create when we go from the eyes to the bottom of the mirror you can basically double that. So these two angles would be congruent. And what I end up here with is an isosceles triangle. Here's the top half of the person, here's the bottom half of the person. So the mirror has to be half the height of the person in order to see the entire body. Let's try an example for a double mirror. We're going to use the same process again, and I'm going to use my shortcut of a perpendicular bisector. So I'm putting my ruler perpendicular to the mirror, and I'm starting with the object. And I'm going to draw an image, my first image, equally distant on the other side of the mirror. Okay. Next, I'm going to do the same thing with a second mirror. This picture is similar to what happens when you would say look in a three-way mirror in a department store. Now notice that I have put my ruler perpendicular again, and I'm measuring here 1, 2, 3, 3.4 centimeters. 1, 2, 3, 3.4 centimeters is right about there. I'm sketching my image. Image 1, image 2. Now if the person is truly using two mirrors to see the object, then I'm going to draw a line from their eye to the second image. This is what they think they see in the mirror. And again, what's really happening is the light is bouncing off of two mirrors. So now I'm going to go back from this intersection of the light ray and the mirror. I'm going to go to image 1. So here I am going from this intersection to image 1. Finally, I'm going to go from the intersection of the mirror to the object. Now look at the picture and see if it makes sense. Do the light rays appear to obey the law of reflection? In other words, if I draw in the normal, do I get equal angles? It appears that yes, I do. And I also want to point out that because of the geometry that we've done here, because we've essentially created two isosceles triangles, in other words, this side is equal to this side, and then for this big triangle, this side is equal to this side, we have ensured that the angles are the same. And so we have ensured that we're following the law of reflection. Let's try one more example. Okay, so let's do the steps. First, let's create that perpendicular bisector. Ooh, I'm in inches. Comes out to exactly ½ inch. Again, I'm starting with the object, sketching image 1. Then I'm going to extend my second mirror because it's not long enough. I'm going to reflect image 1 over my mirror. Here's image 2. And then to draw the full ray diagram, I go from the observer to image 2. Okay, that's a real light ray. This should be a dotted line. Then I go from this intersection back to image 1. Then I go from this intersection back to the object. So the beam of light bounces off of the object, off both mirrors, and goes to the person's eye. And again, I'm looking to make sure I obey the law of reflection. Another way to check the law